So, hello, welcome everybody to our 6th lecture on convex analysis. So to get started, there are 3 questions in chat, and it looks like there's no answer yet. Actually it's not really terribly necessary that we discuss these questions right now. Maybe I have a look later on when I see some question. In case you already answered and it's just not showing me, maybe you can just also drop a note. So after my faux pas yesterday, where I screwed up that proof of these characterizations of convexity for once or twice differentiable functions, I loaded up that video yesterday afternoon where posted this complete proof. They are actually not that difficult, so you may watch this video in case you haven't done so already. Okay, so then let's go on for convex analysis. So the topic of today is these continuity properties of convex functions and existence of minimizers. We talked about the existence of minimizers in the questions yesterday already, and have seen that both convexity and lower semi-continuity alone are not enough. Even together they are not enough, and we need something else. Okay, so but first about the continuity. So so lecture 6, continuity of convex functions and minimizers. So it's not continuity of minimizers, but existence of minimizers. Convexity implies a notion of continuity, a certain type, which I always find a little bit surprising, because convexity is defined just merely algebraic. So it's we only need that this one inequality holds for all. So it's just one inequality, but nevertheless, we will be able to deduce something about continuity, and we will see how exactly the topology enters the game, because there's no topology in this statement. There's only vector space operations and there's a function mapping to the real line or extended real line. So, and the magic is probably that you can deduce continuity of a convex function if you know that it's bounded. Okay, there's the first answers. Okay, maybe I first treat the first lemma and then we have a look at the questions. So boundedness of f is enough to conclude continuity. But so now we allow the value f of x to be plus infinite. And of course, f may also go to plus infinity at some way. So, and then if this happens at a point, then continuity is an issue, and you can't kind of deduce this. So the first lemma is to show that if a function is bounded near a point and convex, then it's also continuous at that point. Okay. And then there you have it. There you have a local property, and local is defined in terms of a topology or a metric or whatever. Lemma 6.1. So if f from Rd to R bar, so extended real line, is proper and convex, and locally bounded at x0. So what does that mean, locally bounded at x0? This means there exists a delta, non-positive delta, and constants m, small m and capital M, real constants, such that whenever x is in the ball around x0, and I now induce here the radius 2 delta for technical reasons, then it should hold that m is a lower bound and capital M is an upper bound. So on a ball of radius 2 delta, the function values lie between small m and capital M. And then f is not only continuous but even Lipschitz continuous. Then f is Lipschitz continuous on the ball with radius delta, and that's the technical reason why I needed 2 delta here. You only get half the radius down here, is 0 with Lipschitz constant at most. This is now capital M minus small m divided by delta. So on, that's the statement, and there's the or here, this is where the topology comes in. If we have a neighborhood of f of some point x0 where we have boundedness, then on the neighborhood of half the radius, we have Lipschitz continuity, and this is the Lipschitz constant, and you see this Lipschitz constant can explode in various ways. So it can explode if you make the region larger so that the upper bounds or the lower bounds deteriorate. So you can send this to plus infinity, for example, by making the ball larger, but also by making the ball smaller, delta getting smaller, this guy may explode. So in various ways, this is a local statement, and the bound does not give anything global in that way here. Up to now, we will come to something more stronger later. So yeah, local boundedness is like, so if you have here the domain of definition, somewhere we have an x0, and here's then function value f of x0, and what local boundedness means, we can find a neighborhood here, x0 plus 2 delta, x0 minus 2 delta, such that on this neighborhood our function is lower bounded and upper bounded. Okay, and then we will get Lipschitz continuity, and this kind of looks like, yeah, well, why shouldn't it? So this, but this is not, yeah, okay, it can be very steep in here still. Okay, let's see how we get that. Okay, the proof. I avoided it's a bit technical, but in the second thought, it's not too technical. It's just shoving around a few inequalities, and then you're done. So we want to show Lipschitz continuity on that ball. We take 2 points in that ball, and we want to use Lipschitz. We want to use convexity. So we should introduce some way of a convex combination. So and of course we assume that these points are not the same. And what we do is, so you can use convex combinations of these 2 points, but this will not bring us what we want. We have to move a little bit further outside of this ball to get what we want. And what we do is, so maybe I find, so if I paint a two-dimensional picture here. So this is our point x0. That should be the ball of radius delta, and then this will be the point, the ball of radius 2 delta. Okay, and we have taken 2 points here in this ball, x1 and x2, like this. And what we're going to do is we move a little bit outside of this ball to up here, and then write this x2 as a convex combination of x1 and the point outside here. But we still can work with bounds on the larger ball. So what we do is we define y as 1 plus delta over the distance of x from x1 to x2 times x2 minus delta over the distance from x1 to x2 times x1. That should be x1 actually. And if you have struggle realizing where this point is here, same holds for me. It gets a little simpler if you write it like x2 plus delta times x1 minus x2 normalized, x1 minus x2. So that's the same thing. And now this is probably clear what's happening here. We get y by starting in x2, so starting here, and then moving in the direction from, is it correct? No, that's not correct. It should be 2 minus 1 actually, right? This is the positive, that's an negative, it should be 2 minus 1. That would make more sense. Okay. So x2 minus x1. So we start in x2 and move into the direction from x1 to x2. So this is the direction from x1 to x2, normalized. So from here we move this some way in this direction, and the length here is delta. So here, up here, there's y. And of course, because we defined y to be on that line here, we can write x2 as a convex combination of x1 and y. It's somewhere on the line from x1 to y. Okay, so then we have two things. One thing is that the distance of x1 to x2, x1 minus y minus x2, sorry, y minus x2 is actually this. This is normalized, so this is actually delta. And hence we have that y is in the ball of radius 2 delta around x0, because x2 has distance to x0 by delta, and this is also delta, so the distance used by triangle inequality at most 2 delta. So that's one thing. And the second thing is we can write x2 as a convex combination of x1 and x1 and y. You could do that by rearranging here, and if you do it, so kind of solve this here for x2, you end up with x1 minus x2 divided by delta plus x1 minus x2. These are all two norms, and I realized that somewhere I've forgotten one of these two indices, plus delta over delta plus x1 minus x2 squared x1. So and this is a convex combination, right? So adding these two coefficients here gives 1. And then negative. That's actually a convex combination. It's clear from the picture, and these are the coefficients. Okay, so now we have a convex combination for some point in this ball, and we're going to use convexity. So f convex now implies if we take f of x2, so this is the point where this is the convex combination, and then it's then smaller or equal to this coefficients times f of y. So x1 minus x2 over delta plus x1 minus x2 times f of y plus delta over delta plus x1 minus x2 f of x1. Okay, so why is this good? Now, okay, what we really want to have is an estimate for the difference of function values. So we want to have Lipschitz continuity of f. So we want to have an estimate for the distance of the function values of f1 and f at x1 and f at x2. So we just subtract f of x1 here, f of x2 minus f of x1. And what do we get? Now, yeah, we get, if we subtract f of x1 here, we have to subtract 1 from these, but because these are coefficients for a convex combination, if we subtract 1 from these, we exactly get that. Right? We get negative there, of course. So this is the negative of this, because they both sum to 1. So then we get here x1 minus x2 over delta plus x1 minus x2, f of y minus f of x1. Yeah, this minus 1 is exactly minus this. Okay, and now this is good. So now we have here the distance, and we also have here the distance of function values, the distance of points, but there's still a bunch of other terms, but these can all be estimated. So this is smaller or equal to capital M. So if we subtract here, we could subtract a little more, which is minus m. So this both makes it larger. And we could even be so courageous and drop that term here as well, because it's just non-negative. If we drop it, we only make this the right-hand side larger. So this is here is larger equal to 0. And what we get is we had m minus m divided by delta, and this is what's left. And that was the full proof already. Okay. Good, so actually it's not that technical. So then the idea is if we have 2 points in there, we extrapolate it slightly outside, so not so as far as we are still in the ball of the double radius, and then write one of these points as the convex combination of the other two, use convexity, and then our estimates can work out. Okay, nice. So let's continue. Okay, now let's see. There's just one answer, or only okay anyway. But let's still discuss it. So and actually, these are questions which have been answered, I guess, in the exercise class already, or you're still working on it. So here is the question about if a function is convex or not. So we have here a bunch of vectors pi and a bunch of scalars alpha I, can be as many as you like, and I define a function f of x as, unfortunately there's a line break here, the largest what you get if you take the inner product of pi with x and add alpha I. You do this for all the i's, you always get some real numbers for some fixed x, and the supremum of all the real numbers you get. That's your function value. Okay, and is this convex or not? So, well, the picture is like this. Each of the functions inside the supremum is an affine function. So it's a function like that, or a function like that, or a function like that, or a function like this. Okay, and it can be as many as you like. I don't know, on this, maybe even this, or whatever. It can be very steep if you, why not? And what is happening here, it's the pointwise supremum. So what in this example, this would be the function which comes out, and this looks like it's convex, and it actually is convex. Well, why? Because the suprema of convex functions are convex and affine functions are convex. That's already it. So this is, yes, it is. Lower semi-continuity goes by the same argument, because lower semi-continuity is also preserved under pointwise suprema. And we have, yeah, so it's just the same argument. Okay, nice. And what will be surprising maybe to you, or which is far-reaching, is that this is actually everything. All the convex lower semi-continuous functions can be written in this form. That will be an important result in the following. Probably already showed that in the exercise, I guess. So, but working out the details is not totally straightforward. Okay, and there's another question here on strong convexity. And yeah, because I announced that, and I thought, well, if I post the questions a few minutes in advance, maybe you have enough time to think about it. At least make a guess. So the function under consideration is f of x is equal x transpose ax for a positive, for symmetric positive definite matrix A. Okay, and the question, so I announced it's strongly convex, not only convex, but how you see it. Okay, and I would say we diagonalize because it's symmetric. So we have to estimate this from below. So what we need is, how can we show strong convexity? Maybe go some step back. How can we show strong convexity? We know that strong convexity is also characterized by the fact that f of x minus sigma over 2 times x squared is still convex. And if this is true, then f is strongly convex with constant sigma. So what we can try is to estimate this guy from below by a quadratic function with some scalar in front, so by norm squared, h over 2 times some scalar. And if you do that, then the function is still positive. Then we can subtract this function, and the function is still non-negative, and it will still be convex. So we kind of need to find the quadratic lower bound for that function. Okay, convex quadratic lower bound for that function. And what you can do is diagonalization. And so, of course, so if you would try, for example, Cauchy-Schwarz, this does not work. So if you try to estimate from below, so this is exactly ax times x. And if you want to estimate from below by Cauchy-Schwarz, you can only go like this, and this is too much. So this is not giving you anything positive. It gives you a negative lower bound. This is not good. Okay, it's not wrong, but it's not good. So if we diagonalize like this, so this is an orthonormal matrix, this is diagonal, then we get that f of x is equal to v transpose x. Sorry, I wanted to write vx transpose times d times vx. If you inspect that now carefully, what you see is that you can bound this from below a little bit nicer, especially so this d should be a diagonal matrix lambda 1 to lambda n, and the lambda, they are decaying, and the last one is still positive. And what you can see is that this you can bound from below by lambda n times the norm of vx squared, the smallest eigenvalue of A. sheesh. So none of the answers is right. I forgot the 1 over 2. I forgot the 1 over 2, sorry. So none of the answers is right. So if in case if you hesitated, okay, now I get why. So because this y here, because v is orthonormal, this is exactly the norm of x squared, and so our so this is sigma min, actually, is it sigma, lambda, whatever. So this should be the smallest eigenvalue of a times norm x squared. And then we see constant of strong convexity is actually twice the minimum, the smallest eigenvalue. So this should have been the answer, but for some reason I forgot the 2. So both of them are wrong. This is wrong because of the square at least, and this is wrong because there's a factor 2 missing. So if I wrote here over 2, so x transpose x, x transpose ax divided by 2, then this would have been the right answer. And actually you don't need a square. That's what you do, so you don't need that square. You would need that square if you would have started with a different function, norm a of x squared. Then you would get something which is kind of the square of the smallest eigenvalue of a, if I even has eigenvalues, because in this way a doesn't need to be square or symmetry positively finite for this to be a convex function. Okay, so sorry again for getting a detail in the questions. Okay, but anyway, thanks for answering. And now let's move forward with the continuity properties. Oops. So for the continuity properties, the next theorem shows you a little better what goes on with the continuity of convex functions. So if f is proper convex, then f is Lipschitz on any compact subset of the relative interior of the domain of f. So it will never be Lipschitz on the full domain. That is pretty clear by example. So one example is f of x is norm squared over 2. So it's nicely convex, it's strongly convex, but it's not Lipschitz because kind of the distance can only be estimated by the square. So the Lipschitz continuity goes away. So the gradient is not bounded. So Lipschitz would be equal to gradient bounded in the case of differentiability, but the gradient here is actually x. So the norm of the gradient can be arbitrarily large, which you also see by plotting the function. So it goes square norm should look like this. So it gets steeper and steeper and steeper. So it's not Lipschitz continuous. But as soon as you constrain to a compact set, of course, then this function is Lipschitz. Okay, but this is also everything which you need to do. Compact subset of the relative interior of the domain, and then the function is Lipschitz continuous. Okay, let's prove it. And as many proofs where the relative interior is concerned, and as long as there's only one function or only one set involved, we can just forget about the relative interior by arguing so reduction to the full dimensional case. So reduce to full dimensional case where the affine hull of the domain of f is equal to the full RD. We can only work on the affine hull. So we kind of redefine the function that is only defined on the affine hull. The affine hull is kind of linearly isomorphic to another RD with a different dimension, so we could have started with the full domain as well. So we only say that the relative interior of the domain of f is equal to the interior of the domain of f. So note this is only, you can always do that in case you only have one set with which you deal. If you have two sets, then the relative interiors I expect maybe with respect to different affine hulls. So it's not as simple as that anymore. Okay, the second point is we show local Lipschitz continuity. So locally Lipschitz is the second step we're dealing with. Okay. Okay, so we have this compact set, sorry, I wanted to name it C, the compact set subset C, and we start with a point in the compact set C. And now that is still within the interior of the domain of F. So hence we can find the following things. We can find a delta non-negative and vectors v1, let's say, to vr, all in the domain of F, such that the ball of radius 2 delta around x0 is not only contained in the domain of F, so this is one thing because we're working in the interior, we can kind of squeeze in between another set S, which is the convex hull of these v1 to vr, and this is all contained in the domain of F. Yeah, so the picture goes like this. So if we have here our point x0, which is in the interior of the domain, of course we can find a ball around that x0, which is inside the domain, but you could also fit another, let's say an infinity ball around that. Then you would have your 4 points, v1, v2, v3, v4, and we could also fit a ball of this shape inside the domain, because, well, in finite dimensions it always works. So if we squeeze inside this infinity ball, then there's an L2 ball inside this, and then we're done. Okay, so but now the good thing is, if we have a V in this ball of radius 2 delta, we can write it as a convex combination of these points v1 to vr. So we can write V as alpha I vi, I goes from 1 to r, in this case r is 4. Of course, and this is a convex combination. The coefficients alpha I sum to 1 and they are non-negative. So now we have f is convex, and hence we can show that f of v is smaller or equal to, so we use Jensen, we plug in the convex combination, we pull the convex combination out, and everything gets larger, like that. And now the nice thing is that we can bound the function value of any point inside here by only a finite number of numbers here. So the finite number of function values are this, and that point. So all of these things can be bounded by the maximum of f of vi, of course, and I goes from 1 to r. If you do this, then you can pull it out of the sum, because this does not, so let's use a j here, and the sum over the alpha I evaluates to 1, so it's actually bounded by the maximum of f of fj over j. And this is how now we define a capital M, and now we've shown that f is actually locally finite at every point in the relative interior of the domain. That's actually a result which is interesting on its own. I could have stated this actually as a proposition before, because it's important. So convexity implies a kind of local finiteness, but only on the relative interior. Okay, that's already nice. So if you have a convex function and only look in the relative interior of where it's finite, it has to stay finite in the neighborhood of that point. Of course, it does not hold if you omit the interior, because the function may jump up to plus infinity at some point. So that's a convex function jumping up to infinity here. At this point it's finite, but on no neighborhood it's bounded from above. It has infinite values just right there. Okay, so we have an upper bound already, and if you would now have a lower bound for f also, then you would be done. Okay, does the same trick like this work here? No. You can't argue in this way at all, because, well, convexity only goes one way. So convexity, Jensen only goes this way. Sorry. So you have to use a different technique here. So because convexity has kind of a direction, the convex functions bend up like this. So they look like smiles and not like frowns. So they bend up like that. Okay, so here we have used kind of this property here, but we have a property from below. We have affine functions from below. Okay, and we're going to use this to bound from below. Okay, this was proposition 5.4, says there exists P in Rd and an alpha in R such that f of x is larger or equal to x times P plus alpha. So convex functions have affine lower bounds. Okay, but if you now evaluate this lower bound on the ball, it stays finite there. So and then it continues, and if you close the ball, we have a continuous function on a compact set, so the minimum is also obtained. So on this shows here f is bounded from below. Maybe I write it like here. So okay, then so we can write f of x is smaller or equal to the minimum. Actually, we can write minimum over norm x minus x0 2 smaller than delta over this. Minimum exists, compact, continuous, and this is what we define as our M. So we have boundedness from above, boundedness from below. So lemma 6.1 implies f Lipschitz on, oh, and this is actually wrong, it's only Lipschitz on the smaller ball, right? So okay, only Lipschitz on the smaller ball, on the ball B delta x0. Okay, so that was half the way, and now to close everything up, we just need to show use compactness. We didn't use compactness, but now we have a local property. Step 2 global is fairly obvious. So Lipschitz on for C. This goes like this. Step 2 implies that for all x0 in C there exists a Lipschitz constant. There exists a delta depending on x0 and non-negative, and Lipschitz constant depending on x0 and delta also. Yeah, of course non-negative. This is positive, this is non-negative, such that for all x and y in a ball of radius delta around x0, you have f of x0 minus f of y smaller equal to this Lipschitz constant times the distance. Okay, do we cover C by all the B delta of x0, and C is compact and hence finitely many the delta here down here depends on x0, so I forgot to indicate that. Probably it's not that important for you, but anyway, this depends on x0, and the same here. So finally many of these are enough. So compact, maybe I should take compact, and hence finitely many are enough. So let's say B delta x1 around x1 and so on until B delta whatever, what did I write? X capital K or something, x k. And then now it's simple to see that you can just stitch the Lipschitz constants together. Just define L as the maximum, and it's only finitely many of L of x k delta k from 1 to k. This works as a global Lipschitz constant. Okay. So that's nice. Convex functions on compact sets are actually really Lipschitz. And there's now a nice corollary, which is really immediately corollary 6.3. is the following again for proper and convex. So we can't deduce global Lipschitz continuity even on the relative interior, but we can at least deduce continuity. So this is proper and convex. Then f is continuous on the relative interior of its domain, but not so. But I think if you're working with continuity here, we still have to say that the continuity is with respect to the affine hull of the domain. So we only consider continuity within this space here. Okay, so that's immediate. So yeah, if it's Lipschitz continues on every compact, it's continuous on the full space. And one nice thing is, especially if f goes from Rd to R. So I note that this is here finite everywhere. It only assumes finite values, so never the value infinity never appears, and of course minus infinity also. Then we have that proper and convex even implies continuity. Also f continues on the full space. And that's kind of remarkable, right? If you have a convex function which is just assumes finite values, so you only have convexity and finiteness, you have continuity everywhere. Nice. Okay. Okay, good. So, okay, this was the topic about continuity properties of convex functions, locally Lipschitz, Lipschitz on compact subsets of the relative interior of the domain, and kind of continuous on the on the relative interior with respect to the affine hull, and finite values give continuity everywhere. Good. So I think it's time for a break, and then we will be back in 2 minutes after a few of these, 8 more of these jokes. So see you in 2 minutes. Okay, welcome back. Let's go for the second half of that lecture here. It's about minimizers. Okay, what do we want to do with minimizers? So now we start really thinking about problems like this minimize f of x over x in the RD. And f goes from RD to R bar. So maybe this looks simpler as you've seen in the introduction to optimization, because they had to deal with constraints. In our case, we hide this everything. This is kind of as general as the general optimization problem, because the constraints are hidden here. But actually, we only treat problems which are much simpler than the general optimization problems, because we only deal with convex functions. So of course we can introduce constraints by considering f of the form convex function g, which is finite everywhere, plus can we? No, it could also be plus indicator function, for example, like this. This would then model a constraint. For example, we also may have functions f which tend to infinity in a finite horizon, but this can all then be dealt with in this case. So and then the ridiculously large class of problems can be just written down like this: minimize the convex function over a d-dimensional space. Okay, so so in addition of this, what is a minimum, what is a maximum, and so this is a problem which is actually two problems. One would like to find two things. One is the minimum itself as a real number, and the other thing is an x star or x bar which realizes this minimum. So these are two different problems, and sometimes they're one of them is more interesting than the other. It really depends. So, for example, if you think of kind of applications in economy, we would really be interested in what is the minimum value which we have for something, what is the cheapest way to do it. But then the x also tells you how to do it. So the x kind of model your knobs, which you can turn, your system, whatever that is. And so the minimizer x tells you how to tune your knobs. And the minimum f of x shows you what you have to pay for that optimal state. Okay, so this is called so let's say let's do it like this, f star, which we define as the minimum if it exists, f star, the minimum of f of x over x in RD. This is the minimum of f. And if we have f of x star is equals f star, this is the minimizer. So these are two different things, right? The minimum and the minimizer. And what we're going to need is the set of all minimizers. So not only the operator min, which gives out the real number, which is the smallest possible, and the argmin of f is defined as the set of minimizing arguments. So these are just the x hats. Of course, they come from the domain of f with the property that f of x hat. And now, because if we don't know beforehand that the minimizers exist, I could equally just write infimum of f of x over x. This always exists, can be minus infinity, and then still we would like to talk about minimizers in that sense. So this is a set of all minimizers. And if maybe we're going to need it, but I guess not, the set of maximizers is of course the set of minimizers of the negative. And of course there's no flipping here because it's about the arguments. The arguments don't flip around if you flip around the values. Okay, and what you now want to know is conditions on f such that each of these things exists. So for example, does the minimum exist at all? So is the argmin non-empty? If a global minimizer is local minimizer is also global, it's an important question. And another question may be if the set of minimizers contains only one element. So does it contain more than no elements, or contains less than one element? These are both interesting questions. Okay, and as we've seen last time, our actual notions which we now have, convexity, lower semi-continuity, and boundedness, for example, are all not enough. And the prime example is f of x is the exponential function. It's convex, it's even continuous everywhere, it's C infinity, as nice as it can be, and it's bounded from below, but it does not have minimizer. So there's something else needed. And this is something like what happens if you go out. So we have to rule out the possibility that the minimum or the smallest value appear far out of our domain. Okay, and this is our next definition. 6.4, a function f. No, there's something missing here. Function f from Rd to R bar is called level bounded, but actually I prefer the other term, which is coercive in German. If the level sets left for any alpha f are bounded for all alpha. So that's the level bounded function. All level sets have to be bounded. Okay, so that's enough as a property. We don't need anything more than that. Actually, I prefer a slightly different statement of the definition of coercive. So equivalent f coercive if and only if it holds that if some sequence x and x tends to infinity, then it also should hold that the function value tends to infinity. So if you have any sequence such that the norm diverges, then the function values also have to diverge. So it cannot be that far. If you go far out, then you'll be up high. This is what this is. And that's actually equivalent. And let's have a look. Why is it equivalent? So this direction here, from this implication over there. Shall we assume this? Okay, and then we have to show that the level sets are bounded. Okay, so assume that this holds here, and assume that x is in the level set with level alpha of f. So, and this means that f of x is smaller or equal to alpha. So what this now shows, there can't be an unbounded sequence in the level set, because if x would be an unbounded sequence, it has to, in the function values, have to grow over alpha by this here. So if xn, so if xn in the level set of f unbounded, then f of xn has to go to infinity, and this is a contradiction to the fact that the function values have to stay below alpha. Okay, that was just this. Okay, in the other direction, if the level sets are bounded, will be proved by contraposition. Assume it exists some xn with norm going to infinity, but function values not diverging. This then means f of xn is small or equal to c. But then if this holds, we have a diverging sequence, so norm going to infinity, but function values stay below c, but then the level set with respect to this level c of f is not bounded, since all the xn's are in that level set. And that's already it. So if this does not hold, this does not hold, and that's it. Okay, this was supposed to, actually it's very simple. Okay. Good. So and now comes one theorem which says everything which we will need about existence and properties of minimizers for now. It's theorem 6.5. If you have a proper function and convexity is not assumed in general, only properness, then first assertion is if f is lower semi-continuous and coercive, so no convexity assumed, then the set of arc, the minimizers of f is non-empty and compact. So the missing ingredient to lower semi-continuous is coercivity. That's more important for existence of minimizers than convexity. Okay, but if f is convex, and we don't assume anything else, then every local minimizer is global, and the set of minimizers argument of f is convex, but possibly empty, exponential function. Okay, but it's still convex. So if it's not empty, it's also convex. Finally, if f is strictly convex, then it holds that the set of minimizers of f contains at most one point. Okay, and probably the interesting thing is if you put things together. So if you have a function which is lower semi-continuous, coercive, and convex, then both conclusions hold. So then there are minimizers. All local minimizers are global. There are global minimizers, and the set of minimizers is compact and convex. And that's a nice result, right? If you have all these assumptions here, you have a non-empty, compact, convex sets of minimizers, and you don't see any local minimizers which are not global. That's perfect. That's as good as it can be. No, it's not. It's a little better if you even have strictly convex. Then there's exactly one best x which you can find, and it exists always. Okay, so let's prove that. Proof. For the first. So if f is proper, we can define alpha as the infimum of f, and then that will not be infinite because there's at least a finite value. Okay, that's the first thing. And then, by definition of the infimum, that's always a point I stress. By the definition of an infimum, there are points xn such that the function values converge to that minimum. So there exists n xn such that f of xn converges to alpha bar. If this would not be the case, this would not be the minimum, the infimum. Okay, so f coercive now implies that the xn's are bounded. Right? If the function values stay bounded, the arguments have to stay bounded. So now comes one of the big arguments, or the heavy machinery. Bounded sequences have accumulation points, have convergence subsequences. So because x is bounded and we are in Rd, so for bounded functions, there exists subsequence x and k such that not the f's but now the x's. So this we have to conclude from convergence of the functions. You have to conclude something about convergence of the arguments. So these x and k converge to something, and I call that x bar for some x bar. Okay, and this is now a candidate for being a minimizer. So the minimum value, the infimum value is alpha bar. We have no idea where it will be assumed, but of course the limit of xn would be a candidate, but the limit of xn does not need to exist. The sequence xn may wiggle around, but it stays bounded. It has the convergence subsequence, and now the limit of that subsequence. That's now a good candidate for being a minimizer. Okay, so we have used coercivity here. We have to use lower semi-continuity at some point, and the point is now. Since f is lower semi-continuous, we know that the function value at the limit point may even be smaller than the limit inferior of the function along the way for k to infinity. It may jump down in the limit. Okay, good. But the sequence f of xn, that even converges to x bar. So this is a subsequence of this real sequence of real numbers. So the limit inferior is actually a limit, and it's equal to alpha bar. So there we have it. So this shows that x bar is actually in the argmin of f, because its value is potentially even smaller, but it can't be smaller than the infimum, so it has to be equal to the infimum, and that's it. Okay, and finally we know that argmin f is the same as the level set of the smallest possible level, and this here is bounded because of coercivity and closed because of lower semi-continuity, hence compact. And again, we used the fact that we're here in RD, and these 2 points here, so this implication here and this implication here is hence they use the fact that we are working in RD and not in an arbitrary Hilbert space. And then we'll come to this today in the end of the lecture if I have time. Okay, that was that. So second point, okay, proving that local minimizers are global. So let's x bar be a local minimizer. Of f. So what does mean local minimizer? That means of f that there exists a delta, a radius, such that f of x bar is smaller equal to f of x for x in the neighborhood, the delta neighborhood of x bar. Okay, and now we want to show that this already has to be global. Nowhere else we can find this point with a smaller function value. Okay, so we take an arbitrary y in RD and lambda in the interval between 0 and, now comes a little bit weird, delta. Actually, it's a little weirder than that. It should be delta over x bar minus y squared. And if this is larger than 1, we take at most 1. Something like this. But if we do that, so the main thing is that we want lambda to be close to 0. That would be helpful. If it's large, it's not a problem. If it's large, it's a problem. Too small, it's not a problem. So then we have that lambda times y plus 1 minus lambda times x bar is in B delta of x bar. Sorry. You can just check that. If you do it like this, if lambda is not too large, then this is not too far away from x bar, and this is what we want. Okay, but now since f is convex, so we didn't use it up to now, since f is convex, we know that first is and x bar locally minimal, that f of x bar is the smallest thing we can get on this full ball. That's an element in the ball, so we have it, there it is larger. So that was not convexity. Convexity comes next. So this is this is that f is locally minimal. But now we do use convexity and estimate from above lambda times f of y plus 1 minus lambda f of x bar. And now what happens is for example, you could subtract f of x bar on both sides and then divide by lambda, which is non-negative, and you end up with f of x bar is actually smaller equal to f of y. And so subtracting f of x and dividing by lambda gives you this. And lambda is positive. So sign does not the inequality sign doesn't flip. And hence x bar is global minimizer. Okay, that was that. And again, it's kind of coming up with some clever convex combinations so you can use convexity. Okay, and the third point, strict convexity gives you global minimizers, unique minimizers, gives you unique minimizers. That is actually simple. So if x bar and x star are both in the argmin of f, then you can consider the midpoint, x bar plus x star over 2, and by strict convexity, this has to be smaller than 1 over 2 times f of x bar plus f of x star. But this is the optimal value, that's the optimal value, that's twice the optimal value, that's the optimal value, this is smaller than the optimal value. No, that can't be. So this would be something below the global optimum, and this can't be. And that's it. That's actually totally straightforward. So if you have, so this is a contradiction if x bar is not x star. Sorry. So if they are, of course, they can be the same. If they would be have been the same right from the beginning, everything here would be would work out. No. Sorry. Yeah. No. Maybe I should do it correctly. Then I should do it like this. If x star is not x bar, then we can use the convexity, because otherwise this would be the same point, and then the convexity would not give a strict inequality actually. So that's probably where it is if they are different. Okay, so that was everything which is in the lecture notes for today, and I said, well, it's not enough for lecture, but anyway, and I thought for those of you who know a little bit about Hilbert spaces, I just drop a few lines about what is different in a general Hilbert space and what not. And for those of you who don't know Hilbert spaces, now you can get a first glimpse about what happens in general spaces. So now what we're going to treat, so kind of it's a detour, so we'll change color a little bit. So the question is basically, so what changes if we use X instead of RD with Hilbert space X. And so the main message is the only thing which changes are technicalities. Some of them are important, some of them are really just not that important. Right. So what is a Hilbert space actually? What is that? So X is Hilbert space if X is so real. So I usually what's with a real Hilbert space, you always use real. So it's a real Hilbert space if it's an R vector space. So we can scale with real scalars. With inner product. So there's the map taking two arguments from X and producing real numbers, and it has to be inner product, which means it has to be linear on the first component and linear on the second component, and it has to be symmetric. And if you plug in the same thing, it should give you something non-negative. And this always defines a norm by taking the square root of the inner product with itself, and it has to be complete. So complete real vector space is complete with respect to the norm induced by an inner product. Okay, so examples for this, of course, RD with the inner product being X transpose times Y, which means Xi times Yi. That's, you probably know that this is the standard inner product on RD, and it's a vector space that's inner product. Completeness follows because the real numbers are complete, for example. You could equip RD with a different inner product, which looks like this, with a SPD, as symmetric positive definite matrix in the middle. So this would also give you an inner product. Because of symmetry, you can swap the arguments here. It of course is linear in both components, and it's non-negative if you plug in the same because of positive definiteness. So that's it. It gives, and this defines you a norm dependent on this symmetric positive definite matrix. This may be important in the following, but all what we did would also work in this case. Nothing would change much, but always the norm would always be kind of with respect to this A. But anyway, it works. So it gets so, and one thing is that you always have this number D, which is the dimension. And you may have noticed that of all what we did, most things did not depend in the slightest on the D. The D basically appeared nowhere. It appears in convex analysis in Kara-Theodoris theorem, for example, but we didn't treat it here. So all what we did not really depend on D. The only thing which really comes to mind for me is this thing that we used, that the D is a natural number. So it's just D dimensioned, and so we can apply this Heine-Borel thing that bounded sequences have convergent subsequences. And bounded and closed sets are compact. So, but So then it would be nice, if the D does not really play a role, it would be nice to have a theory which allow arbitrary D. And with arbitrary, I mean arbitrarily large. It does, and but how do you deal with the so can you deal with infinite dimensional spaces and spaces which are not finite dimensional? And yes, you can. The standard space would be, it's called L2. That would be the set of all sequences of real numbers. So if I did like this, so it's an infinite number of coordinates, but we have to restrict it somehow to be able to define a nice inner product. And this is, we assume that these sequences are square summable. Only consider these sequences such that the number, the series over the entries squared converge. And what is the inner product? The same as here. Inner product of x and y is just the same. And the norm would be the square root of xi squared. Just that. So this makes no sense because so they are all have finite norms somehow. And by Cauchy-Schwarz applies here in this sense, and this shows you that this always exists if x and y are square summable. And that's a Hilbert space actually. It's complete. One has to do a little bit, but it's not that hard. Yeah. Okay, and another example is space capital L2 of omega on some subset of RD, for example. Actually, it also would work if this would be a measure space equipped with a measure, because what we want to do is that we want to consider functions from omega to R, Lebesgue measurable. MB for measurable. So, and of course, identifying two functions which are the same almost everywhere. And most importantly, we also need to constrain something like the square. The square of the function is integrable. So we saw that the set of equivalence classes, to be precise, of all Lebesgue measurable functions such that the integral over the square of the magnitude is finite. And we have this kind of the same idea for the inner product. We just integrate f times g over omega. This is also over omega. And then the norm of f is just the square root of the integral over f squared. And this is also a Hilbert space. And for completeness, you need this identification if you identify two functions which are the same almost everywhere. Okay, so this is kind of an infinite dimensional RD, and to give it a nice norm, you have to take care that somehow norms are finite, so which means that not all coordinates can be large. This kind of the coordinates in the back have to be small somehow. Okay, and so all what we've done, you could always mostly think in terms of as many coordinates as you like at the same time. Okay, but there's one central difference for me. So there are more subtleties, but the central difference for me is so it's kind of the central difference of, let's say, x and RD. In a general Hilbert space, if you have a function, a subset C of x, which is closed and bounded, it does not imply that C is compact. It does not. And if you want to have an example for this, the unit ball in L2. So all the vectors which have distance 1 to the origin, at most distance 1. That's a bounded set, of course, because distance to at most 1. It's closed if we say that the distance can be actually 1, so the closed ball. But it's not compact. So this is simple to see, for example, by assuming that you consider open covers. And the open covers may be like, so maybe I draw a picture. In 2 dimensions, this would be like, this is our unit ball, and you want to cover it. And what we could do is we cover all these, maybe I use a different color here. We color all these unit vectors here. These are the first unit vector, the second, the negative first, and the negative second. And we also cover the rest somehow. But if you cover the rest small enough, you cannot remove these things. So you cover now the complement, such that you don't cover these points. So if you So, and out of this open cover, you can never remove the covers of the unit vectors here. But there's only 4 of them, because we're in 2 dimensions. There's just 2D of them. But in this here, you have a countable number of unit vectors. So the vector which has a 1 in the first component and 0 everywhere else, a 1 in the second and 0 everywhere else, and so on and so on. It's an infinite number. And you could cover all of these unit vectors with one open ball, kind of small, cover the rest such that no other of these sets, the rest sets, cover the unit vector, and you see you have an open cover, and it does not have a finite subcover. It's just not possible. And it's a very straightforward argument. Okay, and this has the that's important, and then this this conclusion does not hold anymore. Bounded functions need not to have convergent subsequences. And that's actually true for the unit ball, right? If you consider the unit ball in infinite dimensions, then you can write down the sequence of unit vectors, which is in this unit ball. It's closed and bounded, but it does not converge to anything. There's no vector to which the sequence of unit vectors converge. And that's the bad thing. Okay, but, so that sounds bad, but it's not as bad. So the one central difference, and the second is that it's not totally not true, this implication, but the important part is there's 2 notions of convergence. Strong. Converging strongly, meaning, let's do it strong. Strong convergence says xn converges to x in the Hilbert space if the norm difference converges to 0, as in every normed space. And this is called strong because there's another notion which is called weak convergence, weaker than that, and this says it's written by such a harpoon arrow where one of these tips is missing, and this is converging if, for all y in the Hilbert space, it holds that the inner products converge as real numbers. So that's the normal convergence with respect to the norm, and that's the weaker version. It's called weak convergence, and it only needs to only test it against another element of the Hilbert space, and then this sequence of real numbers have to converge always. And it's actually weaker. So there are sequences which do converge weakly to something, but they do not converge strongly to anything. And the prime example is the sequence of unit vectors. It does not converge strongly because it's not a Cauchy sequence, for example. The distance of 2 elements is always something positive, square root of 2. But they do converge weakly. It's not that hard to see, or it is simple to see. For example, if you so one consequence here is that if you test with the kth unit vector, which is actually the kth entry, how do I write this? The kth entry of the sequence xn, this has to converge to this. So an ek is the kth unit vector, so 0s 1 and then 0s until the end. So this is the kth component. So that means that each component, or the sequence of components, has to converge to the right thing. So, and as you know, in d dimensions, that's enough. We have a sequence that's converging with respect to any norm, if and only if all of these components converge. In infinite dimensions, that's not enough. So the sequence of unit vectors, if we have all components converging, then you cannot conclude that the sequence itself does converge. And another example is the sequence of unit vectors. You can just figure that out by yourself. It's very simple. So this is kind of something like component-wise convergence or coordinate-wise convergence. It's a little bit more, but more or less. So this is how I usually picture it. And in the L2 space of function, it's more difficult to see. But what does that can mean? And there's more things that can go wrong. Okay. So what do you have to change now? So for example, one thing one has to change is the separation theorems, because closeness, if you have 2 notions of convergence, you can also have two notions of closedness, because in RD closedness means that convergent sequences stay inside. And now we could consider weakly convergent sequence. And actually, there's also a thing called weak topology, which does not come from any norm or something, and I don't introduce it here. And so you have actually two different notions of closeness. Weak closeness with respect to the weak topology, and weak sequentially closeness with respect to the notion of weak convergence. In our context, only convergence will matter, so all the weak statements which we would be interested in convex analysis only come from the statements of weak convergence. But what do we have here? What still holds in the L2 space, for example, if a set is closed and bounded, closed and bounded, so sequentially closed with respect to strong convergence, then it's weakly sequentially compact. So this is something which still holds. It means closed and bounded set. If you have then a sequence in this set, a sequence in the closed and bounded set, then this sequence has a subsequence that converges weakly to something which stays inside the set. That is weakly sequentially closeness. So it's kind of uses the definition of compactness via sequences, but only with respect to the notion of weak convergence. Okay. So for example, what follows from this is if you have a sequence xn of elements of the Hilbert space and they are bounded, then there exists an X and a subsequence such that X and K weakly converges to X. This is something which follows here. Okay, so and then if you bring now convexity into play, things get more interesting because some things are then simpler than expected. So in general, a closed set need not to be weakly closed. For example, and of course, strong convergence would not imply weak convergence, and then you also have different notions of continuity, sequential continuity. If you have a function maybe into the real numbers, maybe continuous with respect to strong convergence or with respect to weak convergence, and they are different notions actually. Okay, but what is interesting is C is convex, a subset in the Hilbert space. You can see that C is closed if and only if C is weakly sequentially closed. That's interesting here, but only holds for convex sets. In convex, we don't have to be too careful about which kind of closeness we mean. They are the same. And this is an important consequence, because remember that we defined lower semi-continuity with respect to closeness of the epigraph. So a consequence of this is that F convex is LSC if and only if F is weakly sequentially LSC, which means you only need that xn converges weakly to x, and this then implies that f of x is small or equal to the limit inferior of f of xn. So not only weak, so much weaker. So there are much more sequences which are weakly convergent than strongly convergent. Oh, I forgot to say strong implies weak, but not the other way around. Strong implies weak is still true. So that's also nice. And the basic thing is that what's behind, what's the working principle behind is that weak convergence is only defined through inner products. Inner products kind of define half spaces, and half spaces are convex. So that's basically it. So if a sequence converges weakly, it stays on the same side of a given hyperplane somehow. So if this somehow, this was maybe a little bit too vague. Okay, so this is one thing by convex analysis in Hilbert space is still very nice, because you don't have to deal so much about different notions of convergence. So you still have to do, for example, in our in our proof today, you have to work a little bit more, but it still works. Bounded sequence, and you don't have a convergent subsequence, but a weakly convergent subsequence. And then you don't need lower semi-continuity, but weak lower semi-continuity with respect to weak convergence. Okay, and then you still can do the same conclusion. So that's actually very nice. And the last thing I wanted to say about Hilbert spaces is that, for example, the function x, the norm of x as a function is continuous, but not weakly continuous. Weakly sequentially continuous. So if you plug in a sequence which converges weakly, the values of the norms need not to converge, but it is still LSC, and also again weak sequentially, which is the same thing. So it still holds if xn converges weakly to some x, then it holds that the limes inferior of the norm of xn is larger equal to the norm of the weak limit. So, and this may even be a strict inequality. If it would not be, then it may jump down in the end. Okay, that was kind of an excursus. So what happens? So what would be the situation in a Hilbert space? Not much changes, and the thing is that the notion of reconvergence kind of saves the day, because for convexity a lot of things then fall together. Okay, so now for those of you who know Hilbert spaces already, you may go through the manuscript or the lecture notes and see what would need changing. For example, be careful with separation theorems, of course. Hyperplanes still work, kind of, okay. And for those of you who did not know Hilbert spaces before, you have a small glimpse of what happens with Hilbert spaces and why it could be important. And why is it important? Because if you would have worked in a Hilbert space, you would be sure that the dimension of the space does not play a role whatsoever. So it would be the case that all that we've done can be applied in spaces of arbitrary dimension. And sometimes that's important. If you think about learning problems, the D is the dimension, or the number of parameters, for example, to optimize. And it really, really often happens that you have solved a problem with a number of dimensions. Well, could we throw in a few more parameters and solve again? And if then the results which you would have obtained depend on the number of dimensions in a bad way, it may happen that the more parameters you put in, the worse the results get. And so, but this, for convex optimization, this is mostly not the case. You can kind of always work dimension independent. Okay, so, but I'm getting off track here. That was it for today. Thanks for listening. And we see again in the next lecture on next Tuesday. Okay, that's it.